Yep. All right, here we go. Today we're going to look at limits as x is driven to either positive or negative infinity. We've actually done this before already graphically, but we're going to look at it from a more numerical approach today. So what do you think the limit of 1 over x as x goes to infinity is? Maybe take a second, pause the video, and write down what you think the answer is. Hopefully, when you come back, you say that the answer is 0. Now, why would that make sense that the answer is 0? Well, if x is getting larger and larger and larger, then you're going to keep dividing by a larger and larger number. So 1 over 10, 1 over 100, 1 over 1,000, 1 over 10,000, and so on and so forth. That's going to annihilate the top, right? That's going to drive this whole expression to 0. All right. Sometimes people say the answer is negative infinity, which is interesting that they would even say that, but you can think of it this way, right? Think of the top constant here, which happens to be 1, but think of it as like a pizza. All right. And then the denominator, well, that's going to represent the number of friends that come over for that pizza. So this will be the number of friends. All right. So think about it. If you have one pizza and you invite, say, 2 friends over, right? How much pizza do they get? They get half a pie each, 4 slices each. But what happens as the number of friends grows, right? So now you have 8 friends that come over. Well, now they're only getting a slice each. Well, now maybe you have 16 friends that come over. Well, now they're only getting a half a slice each. And so what's going to happen as the number of friends goes to infinity, right? Are you going to get negative pizza? No, the amount of pizza that you get is going to basically diminish. It's going to wither away to nothing. It's going to approach 0. So the limit would be 0, right? And it actually doesn't even matter what this constant is. This could be 1, this could be 1,000, this could be 10,000. It's constant. It's holding steady. So eventually, x, since it's going to infinity, eventually it will annihilate any constant and the limit will be 0, right? And that's kind of like the generalization that we want to talk about here, that the limit of really any constant over x as x goes to infinity is going to be 0. And really, I can say x to any power. As long as the numerator is growing without bound, and then, I'm sorry, as long as the denominator is growing without bound and the numerator is being held constant, then that limit will be 0. So the interesting question is, well, does anything change if x goes to negative infinity? And the answer is no, it doesn't really, right? So again, if x goes to negative infinity, I can have like negative 10 down here and then keep going to negative infinity, negative 100, negative 1,000, negative 10,000, right? So when I'm doing 1 divided by those, I'm getting an expression that's getting smaller and smaller and smaller, and it's still going to 0, right? It's just going to 0 from the negative side. So let me take a second here and show you that on Desmos, all right? So if we go over to Desmos, let's look at this guy right here, right? So what I did is I graphed k over x, and I actually put 1 in. So k is just going to be 1 right now. So 1 over x, this is what the graph looks like, right? And I did 2 tables for you. One is a table showing the x values getting larger and larger. So in other words, going to positive infinity. And observe the y values. They're getting smaller and smaller. This guy here, scientific notation, that really means 0.0001, right? So that's what we thought made sense. Well, what about as x goes to negative infinity? So negative 10, negative 100, negative 1,000, negative 10,000. Well, take a look at these numbers. Negative 0.1, negative 0.01, negative 0.001, negative 0.0001. They're still getting smaller. They're not going to negative infinity. They're going to 0. So what is the big difference, right, between these two problems? So the 2 problems I have right here. They're both going to 0, but if you wanted to be particular, you can say, all right, this expression, this is approaching 0 from the positive side, as seen in the table, and this is approaching 0 from the negative side. Okay. Now, another thing that we can kind of look at here, we can just review really, is the graph, right? So what happens when you make your constant larger? So maybe it's 6, maybe it's 12, maybe it's, as big as I want. What's going to happen here? Well, you can see the table values and you can also see the graph. It's not going to change it. Eventually, as x gets big enough, 1 over x is still getting driven to 0. And you can see it graphically with a what? With a horizontal asymptote, right? So that's actually kind of interesting because that's going to bring us to our next thing, which is this, believe it or not, is how you find horizontal asymptotes, right? So if you want to find a horizontal asymptote of a function, just do the limit of that function as x goes to infinity. right? So in other words, if I did the limit of any function f of x as x went to the right forever, right forever, so positive infinity, and I got some number like b, right? So I didn't get positive infinity. So if I went to the right forever, I'm not getting that it's going up forever. I'm not getting that it's going down forever. I'm getting a number like b. Well, that means that there's a horizontal asymptote at b. Likewise, if I did the limit of f of x as x went to negative infinity. So what's going on as x goes to the left forever? Well, if I'm getting a value, if I'm actually approaching a value like b, then that's going to mean that I have a horizontal asymptote at y equals b. So believe it or not, this is the process to find a horizontal asymptote. If you want to find the horizontal asymptote of a function, simply take the limit of it as x goes to either positive or negative infinity. Now think about what this implies. First, this implies that you're going to have at most two horizontal asymptotes for a function. There could be one going to the right forever, and there could be one going to the left forever. Now, oftentimes they are the same, but they don't have to be. All right. A couple of other things is if this is how you're defining a horizontal asymptote, then you can cross a horizontal asymptote. So in other words, as think about this, if this was your horizontal asymptote, if your function was doing something like this, where as you went to the right forever, it was getting closer and closer and closer to that value, right? We would still say that's an HA, and notice I can cross it. All right. Now, we have this conception, I think, in our head that you can't cross an asymptote. Typically, that's with vertical asymptotes because that's typically where a function's not defined. But with a horizontal asymptote, you can absolutely cross it because we really care about what's going on to the extreme right and to the extreme left, not what's necessarily happening here. So you can cross a horizontal asymptote. For example, give you another example. Maybe it's not as complex as this. Maybe you have something that does that, so I cross it, but now as x gets eventually large enough, I start to level off, right? So we're talking about end behavior, extreme right and extreme left. So that's one. The other thing worth noting, and we've talked about this already, is when you do limits as x goes to infinity, all of your limit properties still hold true. So in other words, limit of a sum is the sum of the limits and so on and so forth. All right. So those are limits as x goes to infinity. So let's just do some problems. Nothing crazy here, but we'll do a couple. And maybe these will be the directions. We'll say find the horizontal asymptote. I'm just going to abbreviate that. Okay. So question one, the function will be, say, 2 plus 1 over x. I want to find the horizontal asymptote for that function, right? So in other words, as I go to the right forever and the left forever, is this function leveling off? Well, now I know how to formally do that. The formal process is to take the limit of the function as x goes to positive infinity, right? So that would be the limit as x goes to positive infinity of 2 plus 1 over x. And now this is what I was saying, all your limit properties hold true. So the limit of a sum is the sum of the limits. So I can write this as the limit of 2 as x goes to positive infinity plus the limit of 1 over x as x goes to positive infinity. All right, limit of 2 is just going to be 2. The limit of 1 over x goes to infinity, that's kind of like that key concept of today, right? The bottom's growing without bounds, so all of this is approaching 0, so you get 2 plus 0, which is 2. So that suggests or tells me that there's a horizontal asymptote at y equals 2. All right, so I can do something like right here. Therefore, there's an HA at y equals 2. Now, it's not enough just to see what's going on to the extreme right forever. You want to go see what's going on to the extreme left forever. And I'm not going to be lazy here. And I'm going to write this as a separate problem. Limit as x goes to negative infinity, right? So that's what's going on to the extreme left. And if you think about it, everything is basically going to look identical, right? Except it's as x goes to negative infinity. So when I break this up now, I still get the limit of a constant as a constant itself. Whether I'm going to positive infinity or negative infinity, that's not going to matter. All right, so I still get 2. And the limit of 1 over x as x goes to negative infinity, the bottom is getting larger in the negative direction. So 1 over a large number is a very small number. Positive divided negative just means it's going to be a very negative small number. So I'm still going to 0 though, right? So this is still going to 0. So I still get 2. So I still have, that same asymptote basically. I basically have one asymptote that's approaching in either extreme right or extreme left, the same thing. Now, could I have been a little lazy and did plus or minus infinity here, noting that these are basically going to work out to be exactly the same? Yes, I could have. But it doesn't always work out to be the same. Sometimes you'll get a different number when you go to positive infinity as opposed to when you go to negative infinity. All right, so you have to be conscious of that. All right, so now let's just take a look at the graph of this just so everything kind of makes sense. All right, so if I pull up Desmos here, I keep pulling up the notes and I don't want to do that. And we'll turn this graph off because we're going to look at that in a second. And let me go ahead and graph 2 plus 1 over x, right? So you're like, yeah, it looks like there's an asymptote going on there. Let me actually graph y equals 2. And then maybe for fun, we'll actually make it dotted, right? And you can see, yep, as x goes to the right forever, it certainly appears from the graph that we're getting closer and closer to 2. So it looks like that there's an HA at y equals 2, and the same thing going in the left direction. And it turns out there is, because we actually did it analytically, okay? So that's all fine and dandy. All right, so the next thing we have to do is, before we do a question, is I want you to tell me what radical x squared is. All right, so do you know what radical x squared is? So, well, this is the graph of radical x squared. Now, you may have said x out loud, but that's not the graph of x, right? You can take a look right here. I put radical x squared, and it looks like I didn't get x. I got absolute value of x, and that is, in fact, what radical x squared is. So we're going to kind of need to know that, all right, when we do this next problem. So radical x squared is actually not equal to x. It's equal to absolute value of x. Now, back in the day, you're like, I remember when we did like simplification problems in my algebra class that we always said that this was equal to x. And it is equal to x, but only when x is positive. All right. In fact, it would equal x when it's 0 as well. But this actually would equal negative x if your x was negative. Now, I just graphed it, so that should be convincing that this is equal to this, but maybe it's not. So you're like, what the heck do you mean? Well, like, let's pick a negative x value. Let's do x equals -2, and let's put it in this expression. So I would get radical -2 squared. So -2 squared is 4. I get the square root of 4. The square root of 4, the principal root of 4, is 2. That isn't my x, right? That's actually negative my x. It's minus -2, right? This was my x right here. So hopefully that seals the deal and you get it now, okay? All right, so now with that said, you have that little review pre-calc stuff in the back of your head. Let's do question 2, which is find the HA for this function. We'll call it g of x equals x over radical x squared plus 1. All right, so there's a long way to do this problem and there's a short way. The long way, I'll mention it, but I'm not going to do it, would be to divide everyone, and when I say everyone, to divide the numerator and the denominator by the highest power of x in its most convenient form. So that would be like dividing by radical x squared. If I lost you, not the end of the world. I'm not going to show it to you that way. The other way you can do it is the following. So again, oh, by the way, I have to do the limit of this function as x goes to infinity. Why? Well, because I'm trying to find the horizontal asymptote, and this is the process, do this limit. And when you do a limit as x goes to infinity, a lot of times you're going to hear me say use the end behavior model. So like almost like a sub function of the function, all right, that allows you to get the limit. So in a fractional expression like this, we would look in the numerator and say, okay, for really large values of x, which term is going to dominate? And there's only one term up there, so that's obviously going to be x. So I'm going to do that. And then now in the denominator, for large values of x, which term dominates? So you know, as x gets to 100, 1,000, a million, does this plus 1 really do anything as x is driven to infinity? The answer is it doesn't. So this x squared term is going to dominate, but we have to remember it's under a radical. So this right here would be my end behavior model. I'm not saying that this function is equal to that function. It's not. But their end behaviors would be the same. Their limits to infinity would be the same. So now, what do I do with this? Well, I can simplify this, right? I just showed you some algebra stuff so that you can use it here. Radical x squared, well, I'm going to go ahead and say, yeah, you're just x. You're like, wait a minute, I thought you just said it's absolute value of x. Well, yeah, it is. But if x is going to positive infinity, that means x is positive, right? So if x is positive, radical x squared is just x. And so this ends up just being, when you simplify it, 1. And what is the limit of 1 as x goes to infinity? Well, it's just going to be 1. All right, so now that's half the story, right? We said you also have to do the limit as x goes to negative infinity when you're finding horizontal asymptotes. All right, so if I do that, let's go get them. Limit as x goes to negative infinity. Again, I'm going to use my end behavior model here. So the term that dominates in the numerator, oh, there's only one, so that's x. The term that dominates in the denominator, it's the same term that's going to dominate for large negative values, okay, which, by the way, they're not always the same. The end behavior model for as x goes to positive infinity, not always the same as the one as x goes to negative infinity, but we'll talk about that another time. But now here is the, oh, I know why you just showed me what you showed me, right? So now how do I simplify radical x squared here? Well, now I have to write negative x, right? And now why is that? Well, because x is going to negative infinity. So x is negative. And if x is negative, the square root of x squared is equal to negative x. And so that would simplify to negative 1. And the limit of negative 1, as x goes to anything, is just negative 1. So that actually means I have two horizontal asymptotes, right? So one to the right is going to be y equals 1, and the other one going to the left is going to be y equals negative 1. Right? You don't believe that? Well, let's go ahead and graph it. All right, so let's give our good friend Desmos a try. All right, so if I pull this up and shut that graph off and do h of x equals, let's do x divided by square root of x squared plus 1. All right, take a look at that. Pretty neat. We do y equals 1. All right, that's my asymptote to the right. So let's go to the right forever. You can see this certainly looks like it's approaching y equals 1. But as I go to the left forever, as I go to negative infinity, looks like it's approaching y equals negative 1. Right? Kind of zoom in on that, kind of see the idea. So there's a picture of a function that has two horizontal asymptotes. All right, so pretty neat stuff. All right, let's do one more problem and we'll be done. So let's now take a look at, oh, we don't want to do that. Let's take a look at this guy. Let's do p of x, and maybe it's our good friend sine x over x, which we're seeing an awful lot of that. So I want to see if that has a horizontal asymptote, right? So maybe I'm going to do the limit of sine x over x as x goes to positive infinity, because that's how you find an HA. If anyone asks you, hey, find me a horizontal asymptote, all right, well, I'm going to have to take the limit of the function as x goes to infinity. Now, this is kind of interesting because you don't see the key concept here. This isn't constant over x. This is sine x over x. And I can't necessarily reduce this, right? And I'm not a huge fan of like chucking in infinity like this. Like what does that even mean, right? Sine of infinity doesn't mean anything. Sine fluctuates between 1 and negative 1. So this is kind of like not really a good thing to write. There's two ways to do this. First way is going to be like an analytical in your head thinking way. As x gets larger and larger and larger, what happens to the numerator? Right? So think about it. Think about the sine graph. It fluctuates back and forth between 1 and negative 1. So it doesn't converge on any value. But I think you would agree that it's confined between, or maybe bounded would be a better word, between negative 1 and 1. So I know it ain't getting any bigger than 1, and the numerator is not getting any smaller than negative 1. So that I know. On the other hand, x is going to infinity. So this is growing without bound. So if you have a number in the numerator that's confined between negative 1 and 1, and you keep dividing it by a number in the denominator that's getting larger and larger and larger, what actually is going to happen? Well, you're still going to get 0. And it's not like constant over 0, but it kind of is, because you know you're bounded between negative 1 and 1, and you're going to keep dividing by a larger and larger number. Now, the crazy thing is, do you know how it would approach 0, right? Because if the top keeps changing sign, right, because it's fluctuating between negative 1 and 1, and the bottom's just going to positive infinity, then this would approach 0 in a weird way. It actually would fluctuate sign. All right, so think about what the graph of that would look like. So actually, let's actually not think about it. Let's do it. So let's go ahead and graph. All right, we'll turn off these graphs that we looked at, and let's graph p of x, and it equals sine x divided by x, right? So you're like, oh, it's kind of tough to see. Maybe I'll zoom out and see. This is a good little practice. See how the window's a little wonky, right? I would kind of shrink down my y. So sometimes the zoom key does both. I don't want that. So maybe I'll do -1 to 1 here. And now I get a little bit of a better picture. And you're like, oh, take a look at that. As x goes to positive infinity, right? These oscillations, they're getting tighter and tighter and tighter. So I am approaching zero, but in a weird sort of way, right? As I keep scrolling over there. So that is, in fact, a horizontal asymptote. So there would be one at y equals 0. And you can see going in the other direction, you get the same thing. So these actually agree. So if I go back to my work here, and this time I will be lazy, it's not going to matter if I'm going to positive or negative infinity. Both of those limits are going to equal 0. Because if I'm dividing by a very large negative number, right, I'm still going to get a number going to 0, and the top is fluctuating sign. So that's still going to cause the sign to change. And it's going to do it in that little oscillatory way. And I think I just made up the word oscillatory. Okay. So that's one way to do that problem. That's not using an end behavior model. That's not using that key concept of constant over x. That's just us thinking about it analytically and then seeing graphically that it jives. Well, it actually turns out that we can show this directly using, right, when all else fails, what can we use? The squeeze theorem. And so how would I use the squeeze theorem here? Well, the good news is, if you remember, when we did the limit of sine x over x as x went to 0, when we used the squeeze theorem to show that that limit was 1, that true inequality that we started with was like a little bit of a bear, all right? Here, not going to be the case. Here, the true inequality that I can start with is that basic one, which is that, hey, listen, I know that sine x is between 1 and -1. And so now if you remember, when you're doing the squeeze theorem, start with your true inequality. Okay, got it. Next thing is get the function you're trying to take the limit of in the middle. So I'm like, you're like, all right, you're pretty close. You just have to divide everyone by x. So if I divide everyone by x now, which I'm going to do, I would get this. The next step is to take the limit of everybody. So take the limit as x goes to infinity of -1 over x, less than or equal to the limit as x goes to infinity of sine x over x, less than or equal to the limit as x goes to infinity of 1 over x. And now if this is going to work, you're crossing your fingers here, this limit here and this limit here have to be the same. And they are. And that's actually our key concept for the day, right? The limit of -1 over x as x grows without bound, that's just 0. Obviously, the one in the middle is what we're trying to show directly. So I'm just going to rewrite it. And then the limit of 1 over x as x goes to infinity, that is also 0. So, all right, think about this. You're saying that this limit is less than or equal to 0 and at the same time greater than or equal to 0. Well, therefore, this limit as x goes to infinity is going to be 0. All right. And again, me being lazy, it actually turns out whether I'm going to positive or negative infinity, that key concept that we saw today, they're not going to change anything. All right. So both of those would be 0. And so therefore there would be an HA at y equals 0. All right. So that's limits as x goes to either positive or negative infinity. The major takeaway here is if you have to find the horizontal asymptote of any function, simply take the limit of it as x goes to positive or negative infinity. And if you get an answer, then that's the HA. Now, maybe I'll do one last, I lied, I'll do one last one. Well, what if you don't get an answer? So in other words, what if the function was x squared? We'll keep it real simple, right? So you're like, all right, I want to find out if that has an HA, even though you should already know it doesn't. So you can do the limit of the function as x goes to infinity, right? What do you get? Well, there's no key concept here. Think about this. X squared, if x is going to infinity and I'm squaring that number, still going to get bigger and bigger and bigger. I'm going to go to infinity, right? Think about the graph of x squared. It looks something like this. So as x goes that way forever, this goes that way forever. This is what I mean when you don't get an answer, right? If you're getting an infinity, that means that there is no HA. So therefore, no HA. And in fact, I could be lazy and do either positive or negative infinity, because whether I'm going to the left forever or the right forever, this graph is going up. Okay, but more to come on this when we specifically talk about polynomials and then behavior. All right, be good.